Hello, everyone, and welcome to this presentation for the ARRL Learning Network, an initiative of ARRL, the National Association for Amateur Radio. This webinar series allows us to connect our experienced members with all of our members so we can share our knowledge and discover new ways to enjoy radio technology and communications. And thank you all for being here tonight. I'm Chris Bickle, K1BIC, the Lifelong Learning Manager at ARRL, and today's webinar moderator. Tonight's presentation is called Designing Coiled Coax Ugly Baluns and is being presented by John Portune, W6NBC. And today's presentation is being sponsored by PrepCom, who we thank for their support. We are going to record the session and it will be available within 24 hours after the session ends. And during the session, we encourage you to submit questions using the question box found along the right side. And we'll try to get to as many questions as possible during the Q&A period that follows the presentation. Before I turn this over to John, we have a quick poll question for you. So let me pull that up. And you should see that up on the screen, asking you about your experience level. You can go ahead and select an answer, and we'll let that stay up on the screen for a few seconds. Give everybody a chance to vote. Votes are coming in, so we'll keep it up there for a little while longer. All right, looks like that's just about everybody. So we're going to close that and then we'll show the results. All right, so we have a little more than half that have experience but can always learn something new. And 37% have no experience, but they'll learn how to get started. And two of the rest of you asked about how do you visualize the main purpose of a balun and what is one. So we're going to close that. And John, it's all yours.
All right, well, welcome everyone. My pleasure to be here today and with Chris and the rest of you. We're seeing today a new and improved version, as they say on the commercials, new and improved version of an article that ran in QST in February of this year, which brought back a tremendous amount of email and also a cover plaque award for me, which was nice. By the way, if you got your cell phone out, that QR code will take you to my connections if you want to make connection with me afterwards. Which I'm always happy to answer your questions. On designing coiled coax, or as they're sometimes known as, ugly baluns. They aren't ugly, they're just big. I think that's why they're called ugly baluns. What are we going to learn today? Well, I want to focus in on, because not many people really have a good answer in their mind, and why we ask the question, how do you visualize what a balun is for? I've asked this question many times and always get the same answer, which is not really a good answer. I'm going to show you what the best answer is. So are you sure you know what a balun is for? It's often not what people think it is. We're also going to answer a question that I keep getting questions on. Well, where do I put the balun? Do I have to put it up at my antenna? You know, questions like that. Or shouldn't it go down at my shack? Also, how much balun do I need? Do I need a great big balun or will a little one do? We're going to answer that question too. But mostly I'm going to show you really quickly, really simply, how to create your own coiled coax balun. It's a piece of cake, believe me. All right. As I've said, many people, many hams certainly have heard the term balun, and they've heard of the ugly balun. Now here's a small ugly balun on a 6-meter antenna that it isn't now, another one's in its place, but there's an antenna out in front of my house, a 6-meter antenna, which had this ugly balun on it. And that's a classical ugly balun, several turns of coax on a form. But although many hams have heard of ugly baluns, coiled coax baluns, they really don't know how to design one, and it's really very easy. Okay, to start with, we need to these are the questions we need to answer when we're going to design a coiled coax or an ugly balun. What kind of a form are we going to put it on? How many turns do we need on that form? What's the diameter of the form should it be? Or is there a diameter that it has to be? How about the length of the coil? How do we come up with these answers? If you can answer these 4 questions, you can build a perfectly efficient coiled coax ugly balun. All right, just quickly, these are the 4 forms of the form of the coax. On the left, upper left, is the most popular one, the one you see most often. It's a piece of PVC pipe, the ham's favorite building material, short of copper pipe, of course. That's also the second most popular ham building material from the hardware store. Piece of PVC pipe. These, by the way, are all 2-meter baluns, ones that will work on 144 and higher, and so they're small. But they're the same design as the bigger ones for HF. On the upper left, you see a piece of PVC pipe. That's a piece of 3/4-inch PVC with a couple of holes drilled in it so to put the coax through, or you can use zip ties. Very popular also is on the lower left. You often see this on beam antennas. The first one of these I saw was on a tri-element beam. Just 4 turns of coax wrapped into a bundle and secured with zip ties. Very popular coiled coax balun. That one is usually called an ugly balun. The upper right, though, is one I really like. It's called the torus knot. Instead of trying to hold 4 turns of coax together with zip ties, just take the wire, just take the coax, wind it into a bundle, a single turn bundle, but then take the coax around the other side and bring it back through the middle. And by doing that several times, you'll create a knot called a torus knot, which doesn't need any zip ties. Very handy. I use this often when I'm designing a new antenna. On the bottom right is a little 3D printed form. I own a 3D printer. Most fun device I've ever purchased. I love it. If you haven't got a 3D printer, you should get one. Great use for ham radio. This is one of 2 balun forms that I did on my printer. This one is for 2-meter stuff. That's our G58, or is it Mini 8? Maybe this form takes either of them. It slips over a piece of 3/4-inch pipe. By the way, if you've got a printer or know somebody that does, and you'd like to have the STL file so that you can print one of these yourself, this 2-meter one or the 6-meter one, just send me an email. I'll be glad to send you the STL file. So those are the forms that we typically see ugly baluns or coiled coax baluns made in. All right, let's get to what I consider the #1 concept of this talk. If you don't take anything else away from this talk, take this one with you. What is the primary purpose of a balun? I've asked this in radio clubs, coffee klatch, ham breakfasts, and I always get the same foggy answer. Oh, I know what a balun is for. It's to change an unbalanced line into a balanced line. Yeah, I agree, that's true. But that doesn't mean anything. Most hams can mouth that expression, but it doesn't really explain what's happening. I have a much better answer for this question. What's the primary purpose of the balun? I never use that one on top. It's to convert unbalanced to balanced. The best answer to what a balun is for, simple, is to choke off the outside shield current in coax, so that you don't have any current on the outside of the shield. That's what all baluns are for, even 4-to-1s, even 9-to-1s, even 7-to-1 end-fed baluns. That's their primary purpose, is to get rid of the outside shield current of the coax and to turn coax, which is unbalanced transmission line, into balanced transmission line. Another way to say it is to eliminate common mode current. This comes from the audio world, this expression, but so I like the blue definition. Purpose of a balun, choke off outside shield current. Learn that one. It's an axiom of ham radio. But let's understand this, why it is. Take a piece of coax, take out your pocket knife, cut it in half, and look at the end. This is what you'll see. You all know this. This is not rocket science. There's the center conductor in red, which is solid or stranded. It's the one wire of the transmission line leading from the transceiver to the antenna. And then the white area is the insulation between it and the outer conductor, which is the shield or of the coax. And outside of that, of course, is the jacket, which I'm not showing here. These are the two conductors of coax, and it's inherently a two-conductor transmission line. But unfortunately, it very easily becomes a three-conductor transmission line. And that's what we've got to stop. That's what the Balun is for, stopping coax from being a three-conductor transmission line, hence unbalanced. Okay, let's understand why that exists. We're going to look here just at the center conductor. As you see, there's the center conductor, and as you see, I'm showing it as a ring. Why? Because of skin effect. RF doesn't flow uniformly on conductors, but on the skin, just on the outside skin. Most hams know this. So on the center conductor of your coax, the RF is flowing just on a thin skin on the surface of that center conductor. But it's also using the outer, not the jacket, but the outer shield. Here's a diagram of what the outer shield or the shield looks like. The shield, unlike the center conductor, has two sides, and it therefore has two possible conductors. And skin effect is what allows it to happen. There can be current flowing on the inside in one direction, and there can be current flowing on the outside in the opposite direction. And that's exactly what happens in coax. And that's exactly why coax is a three-conductor, unbalanced transmission line. And it's unbalanced because of that green outer skin. How does it get there? Well, here's how it gets there. Here's a piece of transmission line now, coax cut longitudinally, so you can see a cross section of it. And you see the three possible wires that are present in it. There's the center conductor. That one's okay, no problem with that one, leading out to the dipole there and on the right and providing current to the bottom half of the dipole. And there's the blue conductor, the inside of the shield or the screen, providing current to the top sections of this dipole. But notice the two yellow dots. What are they? They're the end of the coax. But because the end of the coax is a connection now, the inside of the coax is electrically connected to the outside of the coax at that yellow dot. This is what we call the two-wire to three-wire transition. This is the essence of all Baluns. They can be 4-to-1s or 9-to-1s, but that's another function of the Balun. This is the main function of the Balun, is to get rid of that yellow dot. That's an evil, that's an enemy, that's a demon. You don't want the blue current to flow back down on the inside and the outside. You want it to only flow down on the inside. In other words, you want to keep the coax a balanced line and get rid of that unbalanced outer conductor. That's what a Balun is for. Okay, yes, I agree. It's to convert unbalanced to balanced, but you got to know why it's unbalanced. And this is the reason. The third wire in coax caused by that transition at the end is like taking your dipole here, fed by open wire transmission line, balanced transmission line, and adding another wire and hooking a third wire onto that. What is that going to do to you? Well, it's going to do some nasty things, frankly. It can change all of the three things on the right there. Yes, that outer jacket, if you don't have a Balun up there, might change the SWR. It might change the tuning of the antenna. And worst of all, it might change the pattern of the antenna because that yellow wire is radiating, just like the dipole. In other words, you've got a dipole here with three wires on it. And the whole pattern of this dipole isn't going to be the classical donut pattern that you know if you don't have a Balun up there to get rid of that third wire. All right, how do we eliminate it? That's the big question. That's what the Balun does. That's the purpose of the Balun, to eliminate the 2 to 3 wire transition. And it's simple. Here's the coax again that we saw earlier. And here's how we get rid of the effect of the yellow dots, which is to connect the inside of the coax to the outside of the jacket of the shield. We simply put a blockage in the outside shield. You know, like any kind of a thing that'll block it. There's several ways to do it. The common ways to do it are shown on the right. You can make a coil of the shield. You know, wind it up in a coil. That's the ugly Balun. Or you can use ferrite cores or chokes on the outside shield. And both of those will stop the current from flowing down the outside of the shield. In other words, it will keep the unbalanced 3-wire coax, turn it back into a balanced 2-wire coax, where the action is all occurring inside the coax, which is what we want. That's the primary job of the Balun, and to choke off that outside shield current. You can see why I like this term. Well, here's what coiling the coax does, how it works. It forms an inductor or a coil in the outside, and an inductor has impedance, or better called reactance, in the outside of the jacket, so that that green current can't flow down the outside. If you put a high impedance coil right in the shield on the outside, it's not on the inside of the coax. The inside of the coax goes merrily along doing its job. It's the outside of the coax that has this choke in it, this coil. And that's what it is. It's a choke. I like to call balanced coax chokes. That's what I like to call them. And so it will encounter this inductor as well as some interturn capacity, which will form a resonant circuit. And as most hams know, a parallel resonant circuit is a high impedance. It's a choke, it's a blockage. That's how we get rid of that coax current. Of course, you can also do this if you want. You can go to ferrite or some of the other suppliers of these little snap-on split beads. These are great. I have boxes full of these things, and you just snap them on the outside of your coax, and they make great baluns. And by the way, at the bottom shows you which ones to use. You go to ferrite and buy these, which they sell them for reasonable price. So do several other sources. If you're going to operate on the low end of HF, you want to buy mix 43. That's the ratio ceramic to iron powder or ferrite material. If you're going to run at the high end of HF, you want to mix 31, which is a higher frequency ferrite. Or if you're going to run up at UHF frequencies, HF, UHF, VHF, UHF, you want to buy a mix 31. I have these snap-on Baluns in all these 3 mixes. How many do you use? Well, we kind of get around to that later here. And I'm not going to cover it exactly. That's another topic, but we could cover that later. I want to show you this one. This one's interesting. A friend of mine, a young woman who's a very active ham, built this one. She took a piece of RG8, I think that is, and wound it into a small toroid. But she also put some toroid or some cores. These are 240T cores, I think mix 43s. So she's got a combination of using both toroids and a coil of coax. So this is an ugly ferrite Balun. And again, there's the mixes to use in those cores: 43 for low HF, 31 for middle high HF, 61 for VHF and above. All right, that's concept number 1. Now you realize why I like the term a coax choke, not a Balun. I don't like the term. I wish we'd get rid of it. All right, I'm going to answer this question as to where do you put the Balun by asking you a question. Here's a diagram that I've split and done a little photoshopping on. It's the same mast, fiberglass mast, and some wires to hold it up, and a nice dipole at the top. The one on the left is being fed with open wire line. The one at the right, I've photoshopped in a piece of RG8 feeding that line. My question is, where do you put the Balun in both of these pictures? And is it the same in both? And do you need a Balun for the left one? These are questions I want you to think about. Where do you put the Balun here? Bottom, top? You put it up there at the antenna, or do you put it down at the rig, which is the question mark at the bottom? And do you even need one on the left? These are questions you want you to think about right now. See if you know the answers to these questions. If you should be able to answer it, because the answer is really very obvious. Where is, in both of these situations, the 2-wire to 3-wire transition? Where is it happening? Well, on the right, as we've already seen, the 2 to 3-wire transition happens right at the antenna. So if you're feeding that dipole with coax, the Balun, I hate the term, but the coax choke goes right at the feed point. I'm sorry, you can't put it somewhere else. You got to put it up there or you'll defeat your purpose. How about on the left though? Do we even need a 2 to 3-wire transition or a Balun on the left? Oh, yes, we do. Because what's your rig? Is your rig a balanced system? No, your rig is a grounded, unbalanced system. Right out of the transceiver. Even if you've got an antenna tuner in there, it's still an unbalanced system. Where does the Balun go in the one on the left? It goes at your rig, just at the output of the tuner, if you've got a tuner in line to tune up that open wire line. But you say, I've got a balanced tuner. Oh yeah, don't use the balanced tuner. That Balun inside of there is a bad idea. But the Balun that you want in the left situation does go down at the rig, because that's where the 2 to 3-wire transition. Your rig's an unbalanced 2-wire device. The transmission line is a balanced 2-wire line. That's where you need the Balun if you're running a rig and a tuner down in your shack. On the left, it goes at the top. And we answered it by understanding what that 2 to 3-wire transition is. Okay, enough of that stuff. Very important concept though. Concept number 3, and this is what we're going to finish with today here. How much Balun do you need? This is a big question. I get this a lot from people, particularly if you're going to make an ugly Balun. Well, it has a starting point. And here's the starting point. The coil that you make in your coax by winding it into a toroid or whatever you wind it into, a torus knot or wind it on PVC, it has a inductive reactance. That's the natural impedance characteristic of all coils. It's inductive reactance. Here's the starting point of all balance. That inductive reactance for a Balun needs to be at least 4 times as high as the system impedance. What's the system impedance? That's 50 ohms. Ham systems are 50 ohm systems. So you need a coil with a reactance of 4 times 50 ohms. What's that? 200 ohms. You need a reactance in the coil of your Balun of a minimum of 200 ohms. Can you use more? Oh yes, you can use any amount more practically. But you need to have at least 200 ohms minimum inductive reactance in the choke that you put up at the antenna, or that you put down right after your rig if you're running balanced line after it. You need a 200 ohm reactance coil. Okay, you might ask, is it okay to use more? Yes, it is. For example, if you build a 160 meter Balun, which needs more coil to get that reactance, it'll be okay on the higher bands too. So if you build a 160 meter Balun, it's good for the whole HF band. Okay, here's the math. You'll find this in any radio book, any physics book on electricity and magnetism, that inductive reactance, X sub L, equals 2 pi FL. Famous equation. Well, let's just manipulate it a little bit for the purpose of the Balun. We know that we want 200 ohms minimum or more, but 200 ohms is sufficient reactance. So let's stick the 200 ohms in this familiar equation that inductive reactance is 2 pi times the frequency in hertz and the inductance in henries. or if it's in microhenries and megahertz, it's the same thing. And if we do a little first-year algebra on that equation, it turns into this easy formula. The number of microhenries you need for a coiled coax balun is 31.8 divided by the frequency you're operating on in megahertz. Simple. Anybody should be able to run that much simple math. For example, let's take an example. Suppose you're operating on 30 meters, 10 megahertz. How much inductance do you need? Obviously, 3.18 microhenries. Simple, isn't it? That's the starting point. That's how you get to the beginning step of designing a balun. Figure out how many microhenries you need with this simple basic equation. Learn it. It's a good equation. For your convenience, although you don't need to write these down, you can figure this one out for yourself, or if you're good at Excel, do a little spreadsheet, which is what this is, an Excel spreadsheet. Here's the number of microhenries that you need in a coiled coax ugly balun for the various bands from that very formula that we just saw, all the way down to 160 meters and all the way up to 10 meters. As you can see it, of course, you require less on the higher bands. And of course, you can certainly use that 160 meter balun for all of the bands if you want to, because it's got plenty of reactance to stop the current on the outside. Okay, before I move on here though, notice that top one, 17.7 microhenries. Remember that number. That's the number of microhenries we need for a 160 meter ugly balun. Stick that, write it down somewhere, stick it away in your mind. You're going to need it here in a minute. 17.7 microhenries done from that equation is all we need. Okay, the next step, and this is a little more difficult step, but I'll show you an easy way to do it. Step 2 is you now got to take that number of microhenries, 17.7 we're going to use here in a minute, and you need to turn it into the details of the coil. In other words, how many turns do you need? Anyway, okay, we got the number of microhenries from that coil and that frequency, 17 in case for 160 meters. We now need to turn that 17 microhenries for a 160 meter balun into the number of turns, how long the coil is, and how big the diameter is. And this too is a piece of cake. Okay, if you want to do the math, this formula is in any radio book, in Terman or in Jancic, or you can go to the ARRL handbook and you'll find this equation for what the diameter and what the length of a coil is and the number of turns to give you a certain amount of inductance. But if you want to run this formula, okay, it's got everything you need in it. You just manipulate the equation until you get the one you want out of it. But I don't bother. I'm pretty good at math, but I don't bother with this equation. Here's what I do, and here's what you should do. Here's a wonderful little online calculator. There's the QR code on the right, which if you want to take a picture of, you can, and look at it later. It'll just take you to the URL that you see there at the top, translatorcafe.com, unit converter, US calculator, coil inductance. Wonderful, wonderful little calculator. And there is the calculator on the left. As you can see, it takes what we want. It takes the number of microhenries that we already know from our previous step, and it then takes the diameter of the coil that you want to use, or the form that you want to use, a piece of 2-inch or 4-inch PVC or whatever it is. You look that up on the internet or measure it. And you can also set this one to millimeters if you think better in metric, set here to inches. That little down arrow sets the units. And you also need to know the diameter of the wire. Well, now this is a little trickier because the diameter of the coax is not the outer diameter of the coax because it's got a jacket on it. It's the diameter of the outer diameter of the shield, which is smaller. So you need to cut the shield away and measure the diameter of the actual shield. That's the wire. That's what this equation needs. But it also uses the diameter of the coax, which is the diameter of the insulated wire. Why does it use that? Because that constitutes a spacing between the coil, which changes the inductance or the reactance. Okay, and then all you do is put that in, the number of microhenries the diameter of the coil diameter that you're winding it on, the diameter of the outside of the shield, and the diameter of the outside of the coax. Stick the numbers in this little calculator, press the button, and voila, out of the bottom comes exactly what you need. How long of a coil you need and how many turns. Okay, let's do it. This is the last thing, and this will be the last thing we'll look at. Let's build a 160 meter Balun, an ugly Balun, which you can use on all bands on HF. All right, there it is. 160 meter RG8 Balun. And we're going to wind it on a piece of 4-inch PVC pipe. Look it up on the internet or measure it. 4-inch piece of PVC pipe has an outer diameter of 4.5 inches. PVC is measured on inside diameter. So the outer diameter, 4.5 inches, is one of the numbers we need. There's the inductance we need. We got that from the first equation, 17.7 microhenries for our 160 meter Balun. The diameter of the shield on RG8 is 0.38 inches, and the diameter of the whole coax is 0.403 inches. That's with the jacket on it. So you need those 4 numbers. And here they are. As you can see, here's the little calculator. We stuck in the 17.7 microhenries. The diameter of the 4-inch PVC is 4.5 inches. The diameter of the shield is 0.38. The diameter of the coax is 0.403. We push the button to calculate, and voila, out at the bottom pops the magic answer, 16.7 turns. 16.5 will do. If you want to do the extra 0.2, that's up to you. And the length of the coil, 17 centimeters. This one doesn't give it to you in inches, but there's the conversion for you. 1 inch equals 2.54 centimeters. You might find this a little interesting. They got together not too long ago and decided to standardize the number of centimeters in an inch. And it is officially now 2.54 centimeters in an inch exactly, not 2.5400312756 or whatever. 1 inch is now officially 2.54 centimeters. So you can turn that 17 centimeters in length, divide it by 2.54, and it'll give you the length of your coil. But you don't need to know the length, just to know how long of a piece of pipe you need to cut. And that's how you do it. It's really a piece of cake to design one of these coax Baluns. They're just easy as pie. And yes, they're a little bit ugly, but they work really well. And so that's it, folks. I'm going to conclude with a shameless commercial. As they say on TV, let's pause for this important message. If any of you haven't seen my slot antenna book, you're interested in slot antennas, you can find it here. You'll also find it on Amazon. Go to Kindle Books on Amazon and search for slot antennas for ham radio. This book is done pretty well. I'm actually in the process of writing a second one, which is on making foil tape antennas, making antennas with aluminum and copper tape. I've got a whole bunch of them that are going to go in a new book. So, but if you'd like this one on slot antennas, you can find it there on Amazon Kindle Books under slot antennas for ham radio. And that's it.
All right, John, thank you so much for that presentation. A lot to think about, a lot to digest. So if anybody has any questions, go ahead and ask them in the question box along the right side. Our first question, my 6-feeder 3-element Yagi has a T-match, part of which is a Balun. Is a choke Balun at the feed point recommended?
Well, if you've got a Balun up there already as part of some other device, you shouldn't need one.
While we wait for more questions to come in, what are some of the common questions you've received, John, from your QST article?
Well, the QST article, I didn't show how to run the calculator right, and so that's been most of the answers. I haven't gotten a lot of technical questions. I think people liked the idea and understood it pretty well. The only one that I kind of consistently got is the one I think, which is why I showed those two antennas on the same mast and ask you, where do you put the Balun? I guess some people are confused about they think, well, maybe I should put the Balun at the output of my shack. Well, that's true if you're using open wire line, but not if you're using coax. If you're using coax, you want the Balun right at the feed point, because that's where the 2 to 3 wire transition occurs. That's been perhaps the most common question. Generally speaking, though, the readers have understood the principle.
Okay. The Balun you just designed will be self-resonant somewhere in the HF range. Is that any problem?
No, that's another question I've gotten. Yes, of course, the Balun will be self-resonant. If we go back, I don't know, can we still run the slideshow here? Yeah, I guess we can go back here. Yeah, let's go back to that slide right there. Are you seeing the one with the coil?
Yes.
Okay, that's the coil of coax in your Balun. You'll notice that it also has those CD on it. That's distributed capacity between the turns, and that forms a parallel tuned circuit, which is self-resonant. It will typically be self-resonant below the frequency that you're operating, but there's even calculators online that you can calculate it. That's fine. It doesn't matter if the thing is self-resonant. It's just a better choke at self-resonance. That's all. So I wouldn't worry about self-resonance. You might want to check it if you like. I think the piece of software called Coiled 64 will calculate the self-resonance for you. Just so it's not parked in the middle of the band you're operating, I think you're fine.
Okay, next, any particular coax that should or should not be used for a Balun?
I don't see any reason why any coax shouldn't be used. I've used, starting at the bottom, like for 6 meters, I've used RG58, not great coax, but if you don't run very much of it. I've used Mini 8, and that works quite well. I've also, up at HF, tend to run to the larger coaxes, just simply for the power handling capacity. That's the only reason for using one coax over another, is the power handling capacity, or the tendency of the coax to arc through because of the high impedances present. So my recommendation is use as big as you want to, but any kind of coax will work. You might, if you're a real diehard, you might even try some LMR 400, although that stuff is mighty rigid. Although they make a nice flexible version of it. That's great coax. That's what I tend to use most of the time.
Next, should I mount this around my metal tower?
Do you mean near the metal tower?
Yeah, the question was, should I mount this around my metal tower? I guess it must mean near my metal tower.
Yeah, I think it means near the metal tower. Not really a big problem. Most of the action of this is occurring inside the Balun. Yes, there's some field on the outside, but it should not have a significant effect. I just keep it away from the tower by a small amount of distance. At least the diameter of the Balun should be fine. I can't see any reason for trying to put it many feet away.
Next, isn't it best to make the coils approximately, quote, square, length equals diameter?
I don't quite understand what's being asked here. Circular coils are, of course, have the highest reactance for their size. You can make them square if you want to, but I don't see any particular reason for it.
Next, you mentioned to not use a balanced tuner, but what about a link coupled tuner that is truly balanced?
That's fine. You'll find a lot of modern tuners fake a balanced output. And how do they fake a balanced output? They put a ferrite Balun inside the tuner, and it's usually a voltage Balun. I hate voltage Baluns because they have many nasty characteristics. I don't mind choke Baluns by putting stuff on the outside of the coax, but the typical voltage Balun can become very, very lossy if the impedances that you're trying to match in the antenna are high. So I generally tell people, if you've got a balanced output on your tuner, don't use it. Put a choke balun on the outside.
Next, what about a balun at the shack? Will it keep RF from the receiver?
Well, there's nothing wrong with using more than one balun. You can put them anywhere you want to. You can put one at the shack, you put one in the middle of the coax, you put one up at the feed line. They all do the same thing. They're just a blockage, and you can block it anywhere. But if the one up at the antenna is done well, chances are you don't need one down at the shack.
Is a balun recommended for a quarter wave vertical?
As far as I'm concerned, all antennas should have baluns on them. I put them on everything, because if you'll think about it, if you're that quarter wave vertical against radials is just the radials are just the half of the dipole cut into quarters and spread out. It's still a dipole, and if you feed it with coax, it still has the 2 to 3 wire transition, and the RF will get back on the outside. So yes, a balun at a quarter wave vertical with radials definitely needs a balun at the antenna.
Where does the current go on the outside of the coax?
I'm not Merlin, so I can't answer the question. Where does the current go in an antenna? Well, it flows down the outside of the coax. It depends on how long that coax is, what's at the other end of the coax, what kind of ground it passes over. You know, it's a very difficult question to answer. But in any respect, because of the fact that that outside shield is a partly tuned element, it's going to be part of the antenna. So if it's present there, your antenna isn't just 2 wires up there making a nice clean radiation pattern. Your antenna is a 3-wire dipole with a 3rd wire that's making all sorts of ugly radiation in the wrong direction. So there's no pat answer to where does it go. It makes RF.
Okay, next. I read somewhere that it is important not to let the first and last coils touch when doing an open zip tie coil. Is this a legitimate concern?
Yeah, that's a reasonable idea. That's, I think, principally due to arcing. Because if doing this coiled balun like that, the impedance are going to be pretty high at the end. So I think that's a good recommendation. Keep the ends of the coiled balun separated by a distance.
Next, where is the separation between high HF and low HF related to the ferrite filter?
That one I'd have to do a little research on to give you a quantitative answer, because ferrites are operating in loss mode when they're used as a balun, and I think the answer to that question partly can be found on Amidon's, Bill Amidon's website, amidon.com. You've got to look at the characteristic curves of the ferrite to see where the loss range is, and it'll be where the ferrite has a kind of a rounded curve showing its efficiency and its inefficiencies, and you want to get it so that the ferrite is inefficient on the frequencies you're operating on. That's a complex question, which we could try to answer in a later session. I do have a presentation on that one, by the way.
Next, is current balun better than voltage balun?
In my view, current baluns are always better than voltage baluns. Voltage baluns work in resonant systems. They're good. They work fine in resonant systems. But in non-resonant systems where you've got a lot of reactance present, that's where they can be real monstrous. They have bad loss. So I never touch voltage baluns. Just as that's why I don't recommend the use of the Balun inside of an antenna tuner. It's almost always a voltage Balun. And if you've got a highly reactive antenna out there, in other words, an untuned antenna that you're trying to tune up, that Balun inside the tuner may get as hot as a pistol. I have one of those little IR thermometers, and I've done a lot of probing with it of Baluns, and it's amazing how hot Baluns can get, particularly voltage Baluns, trying to feed a non-resonant antenna. If you've got a resonant antenna, nice properly tuned dipole, and you put a voltage Balun on it, it'll probably work fine. But if you try to tune that 40-meter dipole up on 17 meters, you're likely to blow your Balun up if it's a voltage Balun.
And I have read from some sources that an OCF dipole with a 4-to-1 Balun at the feed point can still exhibit common mode current in the shake and therefore need a 1-to-1 or choke at the transceiver. Your thoughts on that?
Well, that's absolutely correct. I love off-center fed dipoles or off-center fed antennas. In fact, I've built several of them. Had a wonderful one up at my mountain cabin that I used to have. But of course, the 4-to-1 Balun at the feed point will indeed help match this antenna on several bands. So it's a very nice setup. But there's very likely still to be 2 to 3 wire transition occurring. The Balun may take care of it, depends on the design of it. But my personal recommendation is use both of them.
Why is a choke recommended with a 49-to-1 Balun on an end-fed antenna? Won't the Balun work as the choke also?
Well, I like 49-to-1. I like 49-to-1 Baluns, but I got to think about this one. It's an end-fed. You know, I'm going to have to defer this question. 49-to-1 Baluns or 7-to-1 Baluns, 49-to-1 impedance, 49-to-1 turn ratio Baluns are something I want to do a little more work on. That's I have a feeling it would be good to put some ferrites on the coax anyway. Never hurts you to do it. That's why when I'm building a new antenna or trying a new design that I don't know how it's going to work, I just Balun it to death with ferrite choking. What can you hurt? You can't hurt a thing by doing that, and you can't hurt a thing by choking off the end-fed long wire. Chances are the 7-to-1 that's used for the long wire will do the job, but I don't know for sure. That's what I'm going to have to look into more thoroughly.
Okay, no problem. Next, can the Balun be over an aluminum or other non-ferrous metals such as a boom or a mast?
Well, you say, could you wind? Or you mean can you wind it on a piece of aluminum?
Yeah, not quite sure.
Yeah, I think he means can you put it? Can you wind the Balun, the big ugly Balun, and then run a mast through the middle of it? I think that's what he's asking. And yes, that works reasonably well. It will change the choking a bit and change the inductance of the coil, but I don't think that. I think that can be done. That's quite a variable question, of course, a lot of variables in that equation. But I think you could easily wind a 4-inch ugly Balun and run the mast through it coaxially. I don't think that would hurt you.
With a ground-mounted vertical antenna with radials on or just below the surface of the ground, and the coax feed line running on the same plane as the radials, where should the Balun be placed?
Right there at the antenna, because as I said earlier, a quarter wave vertical with radials, quarter wave or whatever radials, is essentially a dipole in which the radials are acting as the other half of the dipole. In other words, the quarter wave that sticks up, the spike, is counterpoised against the 4 radials, which in essence is the other half of a half-wave dipole. They may be resonant or non-resonant, depending upon whether they're above ground or in ground, but there's still the other half of the dipole. So think back to that one slide that I showed you of the balun feeding the antenna. If you need that balun to stop the current flowing back on the shield, you need it there for that antenna, because a quarter wave vertical with radials is a half wave dipole in essence electrically, and if you feed it directly with coax, there's going to be shield current.
Next, what is the best balun to use for a gutter antenna?
The famous gutter antenna. I have one, by the way, except I didn't use my gutters. I find that rain gutters are tough to deal with directly, and you certainly don't want to lay them in the gutter if it's a metal rain gutter. Plastic ones you might. What I did for my rain gutter is I made some little 1-foot standoffs out of PVC pipe to look like vent pipes, and I located 6 of them on the edges of my roof. So when the neighbors look up there, they see they don't see an antenna. They just see some vent pipes, and whoever notices the vent pipes on your neighbor's roof, and then the wire that runs around it is on top of those little vent pipes. But yeah, sure. Well, anyway, a rain gutter antenna is usually a non-resonant antenna. So chances are you can tune it up with a 49-to-1 balun or 7-to-1 balun, or it's a non-resonant piece of wire. There are lots of ways to tune it. So I don't think there's a categoric answer to that.
Next, I see a lot of folks using a 4-to-1 balun with an open wire fed antenna. It should be a 1-to-1 current balun, right?
Well, this is opening up the second aspect of baluns. Baluns have 2 functions. The one that we talked about today here, to choke off shield current, that's its number 1 job. Number 2 job, it can also act as an impedance transformer. If you're trying to feed an antenna that isn't 50 ohms or that isn't 50 ohms, you need some kind of impedance transformation, such as with the off-center fed dipole, which is a lot of 400 ohm impedances up there. So the 4-to-1 balun, if it's a 4-to-1 ferrite balun, will usually perform both functions for you. Will choke off the current and will perform the impedance transform.
Do you ever use 2 baluns together?
Oh, sure. No problem. If you had two 20-meter baluns, they'd probably make a nice 40-meter balun. Just put them in series.
Isn't the balun pretty heavy to put up on top of a tower?
Well, that's why people don't like ugly baluns. I've seen some nice pictures of towers with ugly baluns on them. They're usually mounted on a bracket just below the antenna, and they seem to work fine, but then they're pretty ugly up there. That's why I think most people who run towers with beams and other things on top of them tend to use ferrites for the balun at the top. So I think the ugly balun is an awfully good balun to use on the ground, but they can be used on towers.
And our final question for tonight, what is the difference between voltage and current baluns?
That's a big question, requiring quite a lot of theory and lecturing. Fundamentally, the voltage balun is a transformer, and the current balun is the choke balun, which just blocking shield current. The voltage balun is one that uses the phasing of its coils to choke off the current. That's as simple an answer as I can give quickly. It's a big study.
Okay, that makes sense. As we wrap up, John, would you be able to put your last slide back up on the screen that has your contact info?
Oh, sure. Let's back up here. There it is.
Great. And
now that's the one for my email, if you want, which is also written down there. If you have some So I'll give you a moment or two here to write that one down. If you want that one for the slot antenna handbook, that's this one. But I wouldn't worry about the QR code if you want the slot antenna handbook, which is a whole other topic. Just go to Amazon.com, search for Kindle ebooks, put in the title Slot Antennas for Ham Radio. It'll come right up for you. But there's my personal stuff.
Great. John, thank you so much for all your time in the presentation and answering a lot of good questions. Any final thoughts before we wrap up?
No, my final thought is learn the basic principle of a balun. Don't tell somebody if they ask you, what's the purpose of a balun? To change unbalanced to balance. Don't say it. It's one of those phrases I don't want to hear. Somebody says, what's a balun for? Choking off shield current. That's the answer. Okay, and so put that one in your toolkit and keep it with you.
Great answer. Love it, John. Thank you so much. And thanks again for your time in putting this all together. And a reminder for our participants to visit our Learning Network webpage for a schedule of upcoming webinars and recordings of this and other previous presentations. Go to ARRL.org and click on the webinar link on the homepage or do a search for webinars on the top. Our next session is Learning with High Altitude Balloons. It's being presented by Jack McElroy, KM4ZIA, and Audrey McElroy, KM4BUN, on Thursday, July 22nd at 3:30 p.m. Those are two of our younger presenters, so we look forward to having them join us. So John, thanks again for your time, and thanks to everyone for being with us, and everyone have a great night.
Very well, Chris, and thanks for having, and if I dare say it, best 73s.
Thank you. Good night.